Have you all here. Well, welcome everybody. It is officially time to start our amazing renewable energy event day. We are so excited to have so many schools here from across the nation live with us. We are going to get rolling because we want to get started. I'm sure you guys are eager to get rolling today. And today we have the amazing Engineering Tomorrow program curriculum coordinator, Joanna Cottle, is going to be leading you for the entire day. We have all of our ET staff here as well as our ET engineers to support you. If you need anything, do not hesitate to type in the chat. And I'm going to stop speaking and let Joanna take it away.
Hello, everybody. It's so great to be here with you all today. I'm very excited to talk to you about a subject near and dear to my heart, renewable energy. Let me just quickly start sharing my screen and we'll get underway. Here we go. Hopefully you're seeing that. So a little bit about me. I spent half my career as a mechanical engineer working for a big global construction company called Bechtel. You're going to be learning more about Bechtel from my beloved and dashingly handsome husband this afternoon. But I was fortunate to have two careers. I spent the first half of my career as a mechanical engineer, and then I spent the second half of my career working as a high school educator, teaching physics and engineering at a high school here in Washington, D.C., near where I live. What are we going to be doing today? We are going to be learning how to extract power from wind and the sun by building a hydroelectric power plant. So keep that in the forefront of your mind as we move forward. I'm going to be talking to you today about some of the concepts behind wind and solar energy, in addition to how engineers try to build the best power plant they can. But first, a little bit about me. I was born in England. My parents are both British, and I spent my childhood moving around a lot, because my father was a civil engineer working for Bechtel as well. Actually, he worked for a few companies, but he also worked for Bechtel. Bechtel builds really big, complex projects like big power plants, airports, roads, metro rails, all kinds of things, huge buildings. And so we moved around a lot from project to project as I was growing up. So I was born in England, but when I was 6 weeks old, we moved to Bombay, India. I traveled from there to San Francisco, California, Ann Arbor, Michigan. And then when I was in high school, we moved to Mexico City in Mexico. And I mention this because while it was difficult to move around a lot, I really love traveling and learning about new places. And so I kind of was intrigued by a job in engineering that would allow me to travel and work on interesting projects in new places. And so that was one of the first things I thought about as I was thinking about engineering. Another thing I wanted to mention, you see a lot of pictures of my family here. And I come from a close-knit family. That's the picture on the left. I have two other sisters, one of three girls. But my mom is one of 9 children. And so I have 6 aunties on her side. And me and my sisters are the first girls in her family to go to college. And so I kind of wanted to give a shout out to them because they were a huge cheerleading section for me as I was growing up, and were so excited about when I got into college and what I was going to do next, particularly that I wanted to study engineering, which was something they didn't even think about when they were growing up. So I wanted to add that I hope you all have somebody in your corner, family or friends, who are cheering for you as you make your way through high school and beyond. It's really something that was so important to me as I grew up. So I told you I was in Mexico City when I was going to high school, and I wasn't totally sure what I wanted to do, but I knew that I liked physics a lot, and I knew that I liked physics because it was kind of a mathematical way to solve problems and to model the natural world. I really like the labs and things like that. I hope some of you really like physics as well. So when I started, because I didn't know quite what to do, I did a program that allowed me to explore a few different fields. It's called a dual degree program. And so I started at a small liberal arts school in the mountains of Tennessee called the University of the South. And there I took physics and math courses, but also English and art and other courses, and realized that I really enjoyed physics. And so what this dual degree program allows you to do is study 2 majors and get 2 degrees. So after my junior year, I transferred to Georgia Tech in Atlanta, which was nearby, and I began to take engineering courses to complete the requirements for that major. And again, I was enjoying the physics related courses there, thermodynamics, mechanics, things like that. And so I realized that I thought mechanical engineering might be for me. When I graduated from college, I got a job first with a defense contractor in California, where I was testing satellites to make sure I was testing them in vacuum chambers, the conditions that they would see in space, to make sure that they could withstand those conditions. And while I enjoyed that, I didn't get to know much about what the satellites did or things like that. And I realized that I kind of wanted to have this bigger picture. So I started looking for a job, and Bechtel was one that came up for me again, where my father had worked. And remember, I wanted this, I was hoping I was going to be able to travel and work on big, complex projects. So I got a job with Bechtel. And while I was there, I started to work on increasingly more complex mechanical systems. And I would be in charge of kind of specifying and purchasing, working through the evaluation of the proposals to purchase major equipment. I would work in concert with a lot of other engineers. That's what I love about engineering. It's so collaborative. And a project that I'm particularly proud of is the Sutter project in California. That was a project I was fortunate to be able to go see from just a piece of paper, an idea on paper, and take it all the way through construction and into startup and operation. At the time, this project is located in Northern California near Sacramento. And at the time, it was one of the most efficient and environmentally sustainable plants around. It's a natural gas-fired plant, but it was completely air cooled, so it used very little water, and it recycled all the water that was used in the processes on the plant. I just learned recently when I was looking it up that now this plant is partnering with the EPA to look at a new technology that you might have heard about called carbon sequestration. And that's where a technology where the CO2, the carbon dioxide emissions from a power plant, are captured, they're pressurized, and then they're either used in other processes or they're injected down into porous rock material and stored below the earth as a way to reduce carbon emissions from our total emissions. So that's a little bit about me. I wanted to learn a little bit about you in the context of what your understanding of renewable energy is and energy conservation in general. I'm sure you're hearing a lot about in the news about our warming planet. Perhaps you have been exposed to more severe weather events and have had to deal with the consequences of that. And I know it can all be a bit overwhelming, but I wanted to ask you a few questions and hopefully show you that you are doing things in your own small way to contribute to a big effect of preserving resources on our planet. States and cities in the regions where you live are also making commitments to try to conserve resources and use renewable energy. I know Texas has committed to producing 10,000 megawatts of electricity from renewable sources by 2025. And actually, they report that they've already done that. They've already met that goal. And then California has committed to producing 60% of their electricity from renewable energy by 2030. So I've put together a little poll, and I'm hoping that you can join this poll and answer a few questions about some small things that you might be doing already to conserve resources. So could I ask you to join this poll and answer, see if some of these things are things that you're doing already. Can you see that joining code? So the results are coming in. Easy things to do, turning off the lights. Maybe your family asks you to do that anyway. Lots of us are trying to reduce our reliance of plastic water bottles. Many of us are. I love thrift shopping. I like to try to keep things out of landfills and go to thrift shops. I try to carpool. It looks like a number of you are trying to do that, 30%. And I've put eating a vegetarian meal once or twice a week. Just eating a meatless meal once or twice a week can really cut down on carbon emissions. Looks like about a third of you are doing that. I hope you're seeing that you're doing things already that you can imagine. If everybody does some of these small things, they add up to a lot. Well, thank you. That looks great. I hope you're seeing that as well. One thing I'm not so great at is taking shorter showers. I wish I were better at that, but I'm working on it. I'm a work in progress. I have another question to ask you now, and that is related to whether you see some renewable plants in your neighborhoods. And so I've got another question here, and I'm wondering if you see that. I live in a more urban area, so I'm certainly seeing a lot of solar panels coming up on people's roofs. But I can see, we've got other people who live near different kinds of power plants, and I'm hoping you're seeing those in your communities. California and Washington State have some great hydroelectric plants. Few people are seeing nuclear plants. Those are definitely see those in Texas, California, all over the country. For me, I don't really see wind farms until I get up into the mountains near my home, the Appalachian Mountains. You start to see them on the ridges there. And solar farms. Yeah. Hello? Well, thank you. This is looking great. It looks like quite a few of you are already seeing some renewable plants near where you live as well. So let's find out some more. Let's start going and looking at some of the concepts you're going to learn today. Sorry, there we go. So first, I want to give a shout out to the team that developed this challenge. They are all our challenges are developed by professional engineers in concert with college students. Dr. Eric Einset is an amazing engineer and was the originator of this challenge. And he was helped by Anna from Notre Dame and Jackie from Cornell. We hope that the combination, this team effect, this teamwork of an engineer with college mentors really helps to make these challenges something that feels like it's useful information for you and very accessible, and building skills that you'll be able to take with you beyond into your later years of high school and into college. So what kind of engineers work on renewable energy? Well, the answer to that is easy. Almost all kinds of engineers. Certainly electrical and mechanical engineers are there to help work on the mechanical equipment, and electrical engineers help to make sure that the electricity produced connects seamlessly into the power grid. Civil engineers help to work with the structural components of the power plant. Environmental engineers work to make sure that the power plant meets the community environmental guidelines and also meets the needs of the community. Materials engineers work to make sure that they continually are trying to develop materials that are lighter and stronger to allow the mechanical machinery and solar photovoltaic cells to work more efficiently. And aerospace engineers can help with the wind dynamics over wind turbine blades to make them more efficient as well. So these kinds of complex projects are always worked in teams, and as an engineer, you're always working with engineers of a variety of disciplines to help come up with the final design. Now let's look at some basics. So remember, we're building a hybrid renewable energy plant. So what do you need to know? Well, one thing I want you to be aware of is power and energy. These two words get kind of used simultaneously, and they can be a bit confusing to know which is which. For me, I always think of the idea of going up some stairs in your school. If you go up from the first floor to the higher floors in your school, you're going to use an amount of energy because you're changing your potential energy. You're increasing your potential energy as you go up. But if you run up those stairs compared to walking up those stairs, you're using more power. You're using that energy more quickly. So power, which is measured in watts, is the rate at which energy is consumed or produced. And down below, you've got some pictures. You've got a 60-watt light bulb. A 60-watt light bulb uses 60 joules of energy every second to operate. A more efficient LED light bulb uses 7 watts or 7 joules per second. And there you've got a refrigerator. There you're seeing a measurement in kilowatt hours per year. So that's a kilowatt hour is a measure of energy. It's kind of like the amount of kilowatts over a whole year used. And so kilowatt hours per year is kind of helps you understand how much energy your refrigerator is using. Another kind of unit you're going to see today is a power per square meter, which is often useful in describing the power that is available to be used from the sun or from the wind. So you can see there that the sun uses that can produce 1,000 watts of energy per square meter, and the wind blowing at 1,750 meters per second, blowing at 9 meters per second squared, can produce 1,750 watts of power per square meter. So these are helpful things for you to see and keep in the back of your mind as we move forward. Here's a few other things about wind. So here's some of the major components that you may or may not be familiar with. A wind turbine consists of a tall tower. We like to site wind turbines up higher where the wind blows more consistently and at higher speeds. And so they are often on a tall tower, sometimes greater than 100 yards tall. The nacelle is the where all the gears and the generator are housed, and connected to the nacelle via a shaft are the blades. So the blades spin when blown by the wind. They turn a shaft, and then gears within the nacelle speed up that rotation fast enough so that a generator can produce electricity. So here's a little bit more specific so you can see inside that nacelle. Again, you're taking the kinetic energy of the wind, converting it to rotational energy in the blades, and then a gearbox speeds up that rotation fast enough so that a generator can produce electricity. So you're taking kinetic energy from the wind, rotational energy of the blades, and producing electrical energy from the wind. When we talk about power that you can get from the wind, I would love for you to keep in mind a few key items from this equation. It can look kind of daunting, but it can help you think about your design today when you're building. So you can see that the power in the wind is dependent on the density of the air, but very dependent and very affected by the speed of the wind. You can see that velocity cubed factor in the wind equation. Even a small change in wind speed can really affect the power you get out of the wind turbine. Another thing that I've mentioned before is efficiency. Efficiency, again, is a measure of the useful work or useful energy you get out of a process compared to what you put in. And in the case of a wind turbine, they generally are around 40% efficient. So that coefficient would be 0.4, meaning 40% of the wind energy is converted into electrical energy. Again, engineers are always trying to get higher efficiencies out of their designs. And then the final value you see there is the area. The area is the area swept out by the blades, by the turbine blades. So that's the area of a circle. So I just did an example where the turbine blades had a radius of 60 meters. The wind speed was 10 meters per second. The density of the air was 1.2 kilograms per cubic meter. And the efficiency was 40%. So the coefficient is 0.4. You might see the same calculation in your student interactive workbook today, but I thought you'd be amazed to see that the area swept out, pi r squared, is 11,310 square meters. And when I plug in all the numbers into a power equation, I get 2.71 million watts at a typical wind speed for an average efficient turbine. 2.71 megawatts, which is enough to power 650 homes. And use of this renewable energy source instead of a fossil source offsets 3,500 tons of carbon dioxide emissions. So one wind turbine can power a lot of homes. And you can see that the size of your turbine blades and the wind speed can affect the power that you get out of it. If you were an engineer, where would you think about siting your wind turbine? Well, here's a few examples that engineers have used. You've probably heard some things about offshore wind, particularly in Europe. That is, there's a lot of wind energy offshore. It's becoming more common offshore in the Northeast here near where I live. Here's a wind farm that's, I think, located in Germany. You get a lot of wind off the ocean, so it's a great windy place. Also, offshore wind tends to be located near big cities, so you get, it's easier to get the energy, the electricity to where it's needed. But working in an ocean environment is very harsh on materials, and it's hard to build things out in the ocean. So these types of wind farms tend to be more expensive, but nonetheless effective. And the next picture in the middle is a ridgetop wind turbine range. These are similar to where I live, located along the mountaintops of area mountains. You get lots of regular wind up there, and so that's a good place to site wind turbines. A problem there is that mountaintops are generally in a pretty rural environment. So you need to have access to power lines where you can get the electricity to where the demand is higher, which is in the towns and cities nearby. And then the final picture on the right is the Alta Wind Farm located in Tehachapi, California, on the edge of the Mojave Desert. And that farm is in kind of a unique area where in a desert environment, the hot air heats up and rises off the land. And when that happens, the cooler air from the Pacific comes in to take its place. So there's always this reliable wind coming through this area. And so it's an ideal spot for a wind farm. Another great thing about this wind farm is it's located pretty close to Los Angeles, which has a big energy demand. So it's a very effective wind turbine farm. So now you've got a little more idea about some of the main factors that drive wind turbine performance and how do engineers decide where to put farms. Let's look at solar energy now. So this slide is always pretty amazing to me. If you look at that, the sun emits 23,000 terawatts of energy every year. And that is a huge amount compared to all of the other energy that's used on our planet. And you can see the different amounts there based on the size of the circles. But you could see if we could harness just even a fraction of the solar energy that's available, we could offset a lot of energy use from our finite resources, our fossil fuel resources, and do so much. So there's so much potential with solar energy, and the cost to produce and build solar power plants comes down and down each year. So there's lots of potential out there. The two types of solar plants that we commonly see are photovoltaic plants and solar thermal plants. Photovoltaic plants simply take solar cells, directly produce electricity from the sun's energy, and then that gets sent out to the electrical grid. Solar thermal plants are a little bit different. There you can see on the right these parabolic mirrors, and they're focusing the sun's light on the pipe in the middle. It might be kind of hard for you to see in the picture, but in that pipe is an oil. The sun's energy heats up that oil, and then that hot oil is used to heat water to produce steam and then drive a steam turbine, just like conventional power plants do. So here's a little quick video that'll help you see a little bit more of the specifics on solar energy.
While it may not be the answer to all of our energy problems yet, there's one energy source we have plenty of: sunlight. In fact, the amount of solar energy that strikes the surface of the Earth in 1 hour is more than enough to supply every person on the planet with electricity for an entire year. We currently have a number of methods to harness the extraordinary power of the sun. Most involve converting sunlight into electrical energy. So, how's it done? The most common way to perform this energy swap is by using a photovoltaic cell. These make up the blue solar panels you typically see on people's rooftops. Most photovoltaic or PV cells are made of the element silicon. When a photon or packet of energy from sunlight hits one of the silicon atoms in the cell, it knocks off one of the atom's outer electrons. These free electrons then make their way toward a metal conducting strip on the solar cell's surface. The strip transports this steady stream of electrons, the electrical current, out of the cell so that it can flow into the power grid for people to use. There are other types of solar power as well. Concentrated solar power, or CSP systems, use giant mirrors to direct sunlight onto a small target. The concentrated light is used to heat a fluid, which in turn is used to boil water and create steam that turns an electrical generator. The great thing about both of these solar energy systems is that they are totally renewable and don't emit any greenhouse gases. So, why don't we produce all of our electricity this way? To begin with, solar technologies aren't particularly efficient. Most convert less than 25% of the sunlight that strikes them into usable electrical energy.
So I'll pause it there. We've talked more about efficiency again. Let's move on a little bit to see. Oops, sorry. Next slide. There we go. Let's look a little more closely at that efficiency idea. How can we maximize the energy, the useful energy we get out of a solar cell compared to what the energy that we put in? So again, efficiency is what you get out divided by what you get in. For a 20% efficient solar cell, let's say we wanted to generate 3,000 watts of electricity. How big of a solar array would we need to do that? Well, you can see that you simply you simply follow the math. You take 3,000 divided by 0.2, and you get 15,000 watts. So I need to consume or absorb 15,000 watts of the sun's energy to get 3,000 watts out for a useful electricity. If the sun's energy if the sun can emit 1,000 watts of power over every square meter, then to get 15,000 watts, I'm going to need 15 square meters of solar arrays. So that's how engineers size a solar array panel to produce a certain amount of electricity. Now, the other thing engineers have to think about with solar farms is where the solar farm is going to be located. The sun doesn't shine everywhere equally on the planet. Certainly around the equator, you get much more direct sun directly overhead. But as you move further north or south towards the poles, you're going to get sun shining at more of an angle. So when you think about your solar house today that you're building, it might be interesting for you to try to engineer something that allows you to move the solar panel to better absorb the sun's energy. In real life, a lot of solar arrays have trackers that allow them to track the sun's travel through the sky. So one more thing for you to think about today. So here is what you're going to be having to work with. You're going to have a generator, which is actually just a little motor, but you'll be running it as a generator. You're going to have some LED bulbs, a propeller, which you can use to build your wind turbine, a solar cell for your solar farm, and some electrical connection wires. When you're building the solar part of your hybrid solar power plant, your hybrid renewable power plant, you're going to want to connect your solar panel directly to an LED. When you do that, when you're connecting up an LED, it's important to look at the ends of the LEDs. LEDs are a little bit different in terms of the way they light. Current can only travel through them in one direction in order to get them to light. So they have to be connected from positive to negative. So you can see here in the slide, you're going to connect the red lead of the solar panel to the longer leg, which is the positive leg of the LED. I also took a picture for you to see that the metal connections on the leads are relatively short. If you have some wire cutters in your classroom, it would be great if you could give yourself a little more metal to connect to, but pay special attention to making a good conducting connection between the metal of the lead and the metal of your electrical of your solar panel. And so I've included that picture here. In terms of your wind turbine, your wind farm electrical circuit, here you're going to be hooking your LED up to a different LED up to your generator. And because this little generator is operating as a generator instead of a motor, it means that the positive end, the positive side of the current coming out of the generator is actually going to be from the black lead. So you're going to want to connect the black lead of the generator up to the positive leg of your LED. And speaking of LEDs, you've got a variety of colors in your kit in your classroom. But I wanted you to be aware that the red LED requires the lowest voltage to light up. And for me, when I was testing this, I was able to use the red LED to use my solar cell with, but I wasn't able to get any of the higher LEDs to light with my solar cell. It's a cold, kind of cloudy day here where I am. So even with a light bulb, I wasn't able to get a whole lot of energy, light energy on my solar array. So try a red LED when you're first testing that circuit. When I tested my wind turbine circuit, I used a blow dryer to spin my turbine blade. And from that, I was able to light a blue LED when I tested that circuit. So just some tips on choosing the LED for the appropriate part of your circuit. And here's some inspiration for you. Here's a number of designs from the team that put this challenge together. So you can see a lot of them have the turbine mounted high up, so it better captures the wind that's available. I'm hoping you might have a fan or other things in your classroom you can use, maybe a blow dryer. If not, you can just try blowing on your wind turbine blades when you're testing it. And then hopefully you will be able to get some sunshine or some artificial light in your classroom to light the solar part of your hybrid renewable energy farm. And then when you're going to test it, here's, I'll just play this for you. Here's some testing that went on. So here's somebody's design, and you can see they put their hand over the solar cell and then took it away, and the light lit up. Here they are blowing wind on their turbine, and it's lighting up the red LED there. So other things I'd love for you to look at are, is there a point where you take the wind source away and the light doesn't light? Do you have to have a certain wind speed in order to get your turbine to light? What is the best angle for your solar cell to get maximum exposure to the sun's energy? And I hope that you take lots of pictures, because I can't wait to see what you come up with. I'm really excited for you to get started and start building. And I look forward to seeing all the great designs as the afternoon goes on. Are there any questions before you get started?
If you have any questions at this time, your teachers can type them in chat to us directly. And if not, I think they're ready to build, Joanna.
I think they are too. Well, thank you so much. Thank you. And I hope that you have fun putting this together today. I can't wait to see all your designs.
All right. Well, I want to say thank you to Joanna for leading such a great introduction. I hope that everybody is ready to build. We are going to get started with letting everybody into their breakout rooms. So breakout rooms have opened. We are going to have ET staff along with ET college mentors in the breakout rooms.